So this is the next practice paper for periodic table elements and physical chemistry. So we start off with a multiple choice, and we have to tell which ion has a different number of electrons from the other three ions. So I popped the number of electrons there, and it's gallium which has a different number of electrons, because gallium 3 plus has 28, whereas the other three all have 18 electrons. What is the percentage by mass of oxygen in magnesium nitrate .4H2O? Okay, so you need to include your 4H2O there in your molar mass. Divide it by 160, remembering of course that you have got 6 oxygens there and 4 oxygens there. So 10 times 16 gives you 160. Multiply that by 100% and you will get D. Okay, so number 3, we've got 50 centimeters cubed of 6 mole per decimeter cubed HCl, and we're mixing it with 90 centimeters cubed of 3 mole per decimeter cubed nitric acid, and we need to work out the H plus concentration. So they're both monobasic acids, so that makes it slightly easier for us. So I've got 0.3 moles of HCl, which I've worked out as from 50 times your concentration over 1,000, and I get 0.27 for nitric acid, which of course is 90 times 3 over 1,000. Add them together to give me 0.57 moles per decimeter, 0.57 moles of acid, H plus ions. And that is in a total volume now of 140, which is 50 plus 90 centimeters cubed, and then you need to times that by 1,000, so I'm just going to add another to give 4.1 moles per decimeter cubed. So the answer there is C. So we now need to work out some oxidation states here. So first of all, phosphorus of course here is element, so it's 0. Over here in phosphine, hydrogen is of course +1, and I've got 3 of them, so that means phosphorus must be -3. But here phosphorus is going to be +1, and the reason why is sodium is +1, and hydrogen is +1, and oxygen is -2, and I've got 2 of them give me -4. So I've got a total on this side of +3, and therefore phosphorus must be +1 to make NaH2PO2 neutral. And therefore the element oxidized is of course phosphorus. It is of course reduced as well. It is a disproportionation reaction. Ethene reacts with hydrogen to form ethane. We've got some average bond enthalpies, and it wants to calculate the CH bond. So it's a little bit of fiddliness to work out your CH bond enthalpy. So the first thing is you work out your bonds broken, and I've broken a carbon-carbon bond, carbon-carbon double bond rather, at 612, and I've also broken a hydrogen-hydrogen bond at 436, and I've broken 4 carbon-hydrogen bonds, which I've left here as 4CH. I've made a single carbon-carbon bond of 347 and 6 carbon-hydrogen bonds. And then it's obviously your bonds broken, which I put here, minus your bonds made, which is here. That equals your delta H for the reaction, and therefore rearrange that and you get your answer to be C. Okay, so half-life doesn't matter about your concentration. Half-life is your half-life, which is 20 minutes. So when the initial concentration is 2 moles per decimeter cubed, the half-life is still 20 minutes. So the answer is B. Okay, we've got a proposed mechanism for that reaction. Which rate equation is consistent with that reaction? Well, if you have a look, your slow step here is 2 NO2s, so the correct rate equation is C. Alright, so I now need to work out my mole fraction of H2 in this equilibrium mixture. To do that, I add up all my moles there to give me 1.4, and of that 1.4, 0.960 is H2. So my mole fraction is 0.960 divided by 1.4, which gives me the answer as being B. So I've now got 0.04 moles per cubed solution of a weak monobasic acid is 1% dissociated. What is the value of Kc? So 1% of 0.04 is 4 times 10 to the minus 4. And then Ka, we can say, is going to be the concentration of H plus squared divided by your concentration of the acid. Which is going to be the concentration, which is going to be 4 times 10 to the minus 4 squared, divided by the concentration of your acid, and you get your answer to be B. Which equation matches the enthalpy change of atomization of iodine? I need to form 1 mole of iodine atoms in the gaseous state, and I start from iodine in its standard state, which is I2 solid, so the answer is D. So electrode potentials now. We got a standard cell being constructed from those two half equations, and we have to have one of these statements is correct. So if we have a look, the tin electrode is the most positive, so that will go from left to right, as I've shown, which means aluminium is reversed, and therefore aluminium becoming aluminium 3 plus means aluminium is being oxidized, and the cell potential is the difference between those two values, which is 1.539. Why is zinc not a transition element? It's because there are no zinc ions with an incomplete D subshell. So which of the following statements are correct? Is this a redox reaction? Yes, it is, because hydrogen here is 0, iodine here is 0, oxidation state, hydrogen here is +1 and iodine is -1, so it is a redox reaction. The equilibrium yield is changed by increasing the pressure. That is not true, because there are 2 moles on this side and 2 moles on that side as well. Equilibrium yield of HI increases as temperature increased. That is incorrect as well. It's an exothermic reaction, so the yield is decreased as temperature increases, so therefore only one is correct. Which substances experience induced dipole-dipole interactions? Those are the London forces. It is going to be 1 will and 2 will. Because they will also experience hydrogen bond, of course, but all simple molecules experience London forces as well. Silicon dioxide is, of course, a giant covalent structure, so it doesn't. And finally, for your multiple choice, which of the statements are correct for copper 2+ ions? Copper 2 does not form a square planar complex. It's actually tetrahedral. It can be reduced to copper 1 by iodide ions, and that is the correct electronic configuration for copper 2+, so the answer is C. So we now move on to section B. I've completed your table there for the 2 isotopes of titanium. Obviously both are going to have the same number of protons. There we go there. Number of neutrons will be different, and the number of electrons will be different as well, because this is the 3+ ion. Now I need to calculate the relative atomic mass. So relative atomic mass, as you know, is the relative isotopic mass times the relative abundance as a percent. And you add both of those together and you will get 79.904. And that is the electronic configuration of a bromine atom there. So I've now got to add a few points as I go across period 2 for the first ionization energy, and remember that boron and oxygen are both lower than we expect them to be, so it looks something like that. So why do first ionization energies decrease down the group? It's because down the group the atomic radii increase, and therefore shielding increase, therefore reactivity increases, as there is less nuclear attraction to the outer electrons, which makes them more easily to be lost. Okay, so nice Boltzmann distribution here. Key thing with Boltzmann distribution, don't forget to label your axes. This must always start at 0, 0, You have a little hump and then it trails off. This line here must never touch the x-axis, and therefore they also want two activation energies, one normal activation energy, one of the catalyst, and then this area here which I've shaded is the additional molecules that can react at the lower activation energy. Why is this good? Well, it's because the reaction can occur at low temperature, which reduces the demand on fossil fuels being burnt to produce the energy, which lowers carbon dioxide emissions. It also means that we can develop alternative reactions which produce less hazardous waste. So this is quite a nice question. Wants us to calculate Kp. So for Kp, first of all we need to do is work out our moles at equilibrium. So we start off with 1 mole of methane, 1 mole of H2O, nothing of hydrogen and nothing of carbon dioxide. I end up with 0.2 moles of methane, which means I've lost 0.8 moles of methane, which means I must have also lost 0.8 moles of water because it's 1-to-1 reaction. I've generated 2.4 moles of hydrogen, which is 3 times 0.8, and I've made 0.8 moles of carbon monoxide because again it's 1-to-1 there. Okay, then you need to add these all four together to give you 4 moles and work out your mole fractions and times your mole fractions by the total pressure, which I've done. So you then get your partial pressure of methane here, water, hydrogen and carbon monoxide. Pop that in your Kp expression, which I've done here, and you should get 5184. Your units will be atoms, atmospheres squared, because you've got atmospheres to the power of 4 on the top and atmospheres squared on below, so that cancels with that to give you atmospheres squared. So a nice question for 2 marks, which is just a definition for the enthalpy change of neutralization, and then you've got an ionic equation there. And then quite a nice one again for the complete neutralization of sulfuric acid with sodium hydroxide, which of course gives you sodium sulfate and water. Again, you do need to know your formulae there. It shouldn't really be too much of a problem at A2. And then we're going to work out our enthalpy of neutralization for this reaction. So work out your energy produced, which is going to be your mass of water, which is 50 plus 25, times specific heat capacity times temperature change. Then you work out your moles of sodium hydroxide. Why have I chosen moles of sodium hydroxide? It's because moles of sodium hydroxide is the same as the number of moles of water, so it just makes it a little bit easier. So by doing it per mole of sodium hydroxide, it will also give me per mole of water, which is what I want. That gives me 0.075. Convert this number to kilojoules, which I've done here by dividing by 1000, and you get minus 56.43. Remember your sign there because it's an exothermic reaction, your temperature went up. Okay, so now it wants me to construct an overall equation for the 2 steps as above. So first of all, some of the H2S is reacted with oxygen to form sulfur dioxide, and the remaining H2S is reacted with sulfur dioxide to produce sulfur. So if you times step 2 by 2, you will end up with 2 SO2s on both sides of the equation. So when you add the equations together, the SO2s will cancel to give you this equation. You can, if you like, then cancel this down. So that number would become 2, that would become 1, that would become 2, and that would become 2, like so. Okay, now it's trying to find a mass of sulfur that I can obtain if I get 1.5 times 78 decimeters cubed of natural gas. So first of all, it tells me it contains only 16% of H2S by volume. So I take my volume of natural gas, times it by 60% to give me 2.4 times 10 to the 7 decimeters cubed of H2S. Now I can find my moles of H2S, which is going to be the volume divided by 24 to give me a million. That is going to be the same as my moles of sulfur that I produce, because it is a 1-to-1 reaction, or 2-to-2 here. So that also gives me my moles of sulfur. I then need to times that by 95%, because it's only, well, I say only, it's very good. I get a 90%, 95% yield, to give me 950,000 moles. And then to calculate a mass, finally I times it by the molar mass of sulfur to give me 3.05 times 10 to the 7 grams. Right, so I'm now going to do some delta G calculations. So I put my delta G expression there, which of course you need to know. I first of all need to work out my entropy change for the reaction, which is the entropy of your products minus the entropy of the reactants, which I have done here. Notice that when you do that, that gives you the value in joules per mole per Kelvin, but to use it in this expression here, you need to convert it into kilojoules per mole per Kelvin, which I've done here. Then you pop that into delta G. They've told you delta H for the reaction there, and you need to remember to convert temperature to Kelvin, and that gives you minus 89.96 kilojoules per mole. So it is feasible because delta G is less than 0. Then they want to calculate the temperature at which feasibility changes. That temperature is when delta G equals 0. So when delta G equals 0, you can have this expression here, which if you do that, you get 780 Kelvin. And then finally, they want you to calculate delta FH formation for SO2, which you can do quite easily. You know that delta H for the reaction is minus 145.6, so that equals the enthalpy of your products minus the enthalpy of the reactants, and that will give you the enthalpy of formation of SO2 as being minus 296.8. So we're going to move on to questions about acids now. So first of all, case Ka for vitamin C, which I've done below there, and then pKa for vitamin C to 2 decimal places. So pKa is minus log of Ka, which they've told you here. So you do that, you get 4.17. Okay, so bottle of vitamin C contains vitamin C supplements, contains tablets each with 50 meg of vitamin C. I get 3 of those tablets and make up a solution of 250 centimeters cubed. I need to calculate the pH. So first of all, you've got a mass of vitamin C, which is going to be 3 times 500 meg, which is 1.5 grams. You can find your moles of vitamin C as being your mass divided by the molar mass to give you 8.52 times 10 to the minus 3. To then find your concentration, you need to take your moles divided by your 250 and times by 1,000 there, to give you 0.03408 moles per decimeter cubed. And then if you put it into this expression here, you need to find your concentration of H plus ions, which is the square root of Ka times C. You know Ka, they've told you that up here. You've just worked out your concentration here, which gives you that. And therefore put that in your pH expression and you will get it to be 2.82. So I now need to calculate my ratio of ion over acid in the solution. So pop that into your pH buffer equation, and you put these values here. This is what I'm looking for, this ratio here. You rearrange that and your ratio will be 0.708. Okay, now you need to calculate your mass of the sodium salt. The molar mass of that is 198. So you've worked out your ratio. So in order to calculate your mass, you need to times your ratio by the mass of your sodium salt, which is this number, over 176, which relates, of course, to the 1 there. And then you times that finally by 300, which is your mass of the tablet, and you get 240 meg. And then finally on this page, the sodium salt and vitamin C can be made reacting vitamin C by sodium hydroxide. Aqueous solution of sodium hydroxide has that pH at 298. Calculate the concentration in moles per decimeter cubed of the solution. So you find your concentration of H plus by 10 to the minus pH. Then you can use your Kw expression to work out your concentration of OH minus ions there. And of course your concentration of OH minus ions will be the same as sodium hydroxide, because there's one OH in every one sodium hydroxide. So the first thing we need to do is work out our rate equation. So if we just have a look at our initial rates, you can see from experiment 1 and 2, I have divided by concentration of bromide by 4. My concentration of all the other reactants stays the same, and my initial rate has dropped by 4. So it's first order with respect to Br minus. Now let's have a look at BrO3 minus. Let's have a look at experiments 2 and 3. So we have a look at those. BrO3 minus has been divided by 2, and the rate has been divided by 2, and therefore it's also first order with respect to BrO3 minus. And finally H plus. So for H plus we can look at experiments 3 and 4. H plus has been divided by 2, and the rate has decreased by a factor of 4, so therefore it is second order with respect to H plus. Once you put those, because you've got your rate equation here, rearrange it to find your rate constant K, and you get 12. And then you can rearrange to find your units. Rate is obviously in moles per decimeter cubed per second. All the others are in moles per decimeter cubed. So that cancels, that becomes 3. So your units are going to be moles to the minus 3, decimeters to the power of 9, seconds to the minus 1. To actually carry out these experiments, what you do is for experiment 1, you would mix 10 centimeters cubed of each solution together. That would give you a total volume of 30 to measure the initial rate. And then you would dilute each solution in turn with water, remembering to change the concentration of only one solution at a time and keeping the total volume the same at 30 centimeters cubed. Okay, so we now need to balance this redox equation. If you notice here, manganese changes by +1 there, but changes by -2 there, and therefore this one has to change, so you need 2 of those, which means you'll need a total of 3 of those. And then you need to balance your oxygens and your hydrogens, so you need 2 there and you need a 4 there. Okay, so although MnO42 minus ions disproportionate in acidic solution, they're very stable under alkaline conditions. Why is that? Well, if they're under alkaline conditions, if you add alkali, alkali will of course react with H plus to remove it, which shifts the equilibrium to the left-hand side. However, in acidic conditions, the equilibrium will be shifted to the right hand side because you're increasing H plus ions. So in red I have written the equations for alkaline conditions, and in blue those are the equations in acidic conditions. You need to make sure that they have 4 electrons so that when you add them together, so you need to times this equation here and this equation by 2, which I have done, and when you add them together you will end up with the same overall equation as being 2H2 plus O2 goes to 2H2O, like so. And when you work out the difference between the cell potentials, the cell potential is going to be 1.23 volts. And obviously that's the difference between these two and the difference between those two there. So moving on to some transition metal chemistry there. Electron configuration of ion in +2. Remember the 4s electrons are lost first. Okay, and then we're going to do some reactions of ion. So we start off with the hexa aqua 2 plus ion here, and the hexa aqua ion, which is 3 plus there. To interconvert the two, you need to go this way, you obviously need a reducing agent, and to go this way you need an oxidizing agent, which I have put in, others are available. You add sodium hydroxide, you obviously produce a green precipitate of iron 2 hydroxide, and if you add HCl, it tells you it's a 4 coordinate complex, so you're going to replace the water ligands with chloride. Iron is 3 plus here. You've got 4 chloride ions, each being 1 minus. So you've got iron as +3 here, 4 chlorides, each of -1 there, to give you an overall charge of -1. Okay, so we now need to identify metal M. Okay. So first of all, they've given me a volume of gas collected at room temperature and pressure. So the first thing you can do is convert that into moles. And you have got 6.25 times 10 to the -3 moles of hydrogen there. So if you're using equation 1 here, 1 mole of hydrogen is 1 mole of M. So you'd have the same number of moles of M. And therefore your MR of M, you know your mass that you started with as being 0.188 would be, your MR would be 30.1. If you use equation 2, it is a 3 to 2 ratio, so you figure that out, and your molar mass of M is 45.1. And it must be that one which is correct, because it's the only one that matches the molar mass of a D block element from scandium to zinc, and therefore it is scandium that we are looking for. So part C then, we are looking at some cobalt chemistry there. So I'm taking cobalt chloride, dissolving it in water, getting a hexa aqua complex ion B. I'm then adding ammonia solution to get until no further change, and a pale brown solution forms, and it tells me the ion that it forms. What's an equation for that? So it's obviously a ligand substitution reaction where I've replaced the 6 water ligands with 6 ammonia ligands. The oxidation state of cobalt obviously hasn't changed, it's still +2. And then a nice 3D diagram as shown, which I've done there. Don't forget, each of your ligand bonds must end on the nitrogen, and your bond angle is an octahedral complex, so they're 90 degrees. Right, so final page. Here we go. So first of all, nice empirical formula to work out, which I've done. Gives you 1 cobalt, 6 nitrogens, 18 hydrogens, and 3 chlorines here. You've then got to rearrange that into some sort of meaningful formula. Now you know you've got obviously ammonia ligands there. And it's going to be, they've told you cobalt becomes cobalt 2 plus. So it is the complex which I have drawn there, and therefore the overall complex D is going to have your 3 chloride counter ions here, as I've shown here. So that equals D. So that looks quite complicated. It's actually not that bad, is it really? Okay, finally, half equations and an overall equation for the oxidation of cobalt 2 plus to C by hydrogen peroxide. There's various ones you can do. Obviously, this one's relatively straightforward here. This one's slightly more complicated if you don't remember that one. You've got hydrogen peroxide becoming 2 hydroxide ions, and you need 2 electrons to get that to balance. You then need to times this equation here, the top one, by 2, so you have 2 electrons for there, and add them together, and Bob's your uncle. We have our overall equation here. There are other alternative oxidations of reductions of peroxide that you could use. For example, in acidic conditions, peroxide will gain 2 electrons to become 2 water molecules. But that was probably the most straightforward one for you to use.